This video highlights the automated camshaft key press designed by Team 7 of Grand Valley State University, designed for Engine Power Components. Engine Power Components is the world's leading manufacturer in engine camshafts and balance shafts. So this is Team 7, consisting of Ben Tankey, Elijah Plagmers, Lucas Burkle, Zachary Robotham, Anthony Zimbalati, and advised by Dr. Reffer. So the purpose of the project is to create an automated operation that inserts a Woodruff key into a camshaft and monitors the press force and distance at the same time. The goal is to remove labor that incorporates an operator using a manual press that the company currently incorporates. This adds ease of integrating automation in remaining areas. In the future, EPC plans to incorporate a robot to load the camshafts in the future. The picture on the right shows the key correctly pressed into the shaft so that it is able to rotate in the engine. The functional requirements of our project are that the product must be able to be loaded with a camshaft, orient the shaft so that the key slot is facing upward under the press, present and transfer the key to the press head, press the key into the slot. At the same time, it must record the press force that the press exerts and also record the press distance that the key is inserted into the shaft. Another requirement is that the barcode at the end of all the shafts must be scanned so that our system can connect with the EPC system. This system will integrate with the EP program to receive pass-fail bits. Upon pass bit, release part to production or notify operator if fail bit received. And finally, the cycle time must be under 1 minute. The use case for a project begins with, if no keys have been loaded into the machine, the operator must fill the designated centrifugal bowl with more keys. Next, the operator will grab a clean camshaft that is ready for the key to be pressed. Step 3, the shaft will be loaded into the machine onto the design location. Next, after the keys and shaft have been loaded, the operator must ensure safety and press cycle start. Step 5, the machine will orient both the keys and the shaft. The key will be delivered to the press head where it is held in place using a magnet. At this time, the press will insert the key into the key slot on the shaft. The operator may then unload the camshaft from the location and move the parts to the next station. The key specifications for our project include a maximum and minimum press force of 17.4 kilonewtons and 0 kilonewtons. These values were measured using an FEA and hand calc to determine the interference fit between the key and the camshaft key slot. And the 0 kilonewtons represents an interference fit that is not there as the key is too small and will ultimately fall out of the camshaft. The next specification is the key depth and press distance, maximum and minimum, of 3.52 millimeters and 2.948 millimeters. These values were found using the EPC drawings to determine the distance that the key must be seated into the camshaft to be correctly pressed so that it can fit into the gear. The above specifications are measured using the load cell and the LVDT sensor connected to the press. The next specification is the cost of a $40,000 maximum and a cycle time of 1 minute max. The first step in our process is key sorting. The function here is to sort and dispense keys. An operator loads the bowl with keys, where the bowl begins to spin and the keys are sent outward into the slots. The key orientation is then guided to the exit of the slot. The bowl is designed to hold up to 60 keys and dispensed keys one at a time to be transferred to the press head. As seen above, the key is a Woodruff key, and you can see the design and prototype stages leading up to the final product. After the keys are dispensed from the bowl, they are then transferred to the press head. This is the second stage of key orientation, aligning the keys from the sideways orientation to the vertical orientation in which they are pressed. The pneumatics deliver the key to the press head. The prototype video seen below shows a key that enters the gravity track with a milled out slot, turning into the correct orientation into the stacker where it's sitting vertically. In the stacker, it falls into the arm shown on the right of the actuator with a slot on the end. When ready, the actuator is fired to press forward into the press head, where the key is magnetically held. Here you can see the key being dispensed and pressed forward into the press head. The actuator returns and the key is held in the correct orientation. The next function is shaft orientation. This is designed to orient the shaft so that the key slot is facing upward. The shaft is loaded onto the wheels by the operator. The wheels spin the shaft into the correct orientation, and an actuated pin locks the shaft in place when it reaches that final orientation. The design phase is shown here to the final mechanism. Looking at some of the build progress, this was very early on when the press is the only thing mounted on the table and the cage has been cut down and built to size. This figure shows the beginning of the shaft orientation based on the V-block on the press that orients the shaft. The beginning of the pneumatics are starting to be hooked up with filters and regulators, along with the solenoids used to fire the cylinders. Here you can see the pneumatic package for the press and all of the stands that are used to hold the shaft in place and high enough so that the shaft can sit on the V-block. Now the stands have been started to be put in the correct place with the pin on the end of the shaft. And here is the final shaft product before the pin and the hold down wheel were inserted, with the servo driven shaft connecting to the both driven wheels and the driving wheels and the driven wheels on the side. It is key here to not touch any of the critical surfaces on the shaft, or else it will not be able to function in the engine. So here the wheels are touching non-critical surfaces. And here is the final product with the pinhole actuator mounted on the table along with the hold down wheel, and the solenoids are mounted along with the regulators. Here the pneumatic package is shown along with the main air tube and the manifold that splits the main air into 4 different areas. So the press chosen is used to press the keys into the shaft. This press is a Schmidt press capable of 20 kilonewtons of press force. The maximum stroke of the press is 2 inches with a max pressure of 87 psi. The mount of the press holds the V-block that supports the shafts. The press also incorporates a load cell, press head, and adapters to connect to the ram. To measure the force and distance, the LVDT sensor shown to the right is used to collect press distance data. We incorporate the Kistler 9323A load cell that is used to collect press force data. We have a pass-fail determination using these values that will be measured and tested, and a press monitor to feed EPCO real-time data and use pass-fail parts. So the load cell is the Kistler 9323A. It's a piezoelectric press force load cell with a max of 20 kilonewtons. Here we are using it as an inline force measurement as it's part of the press head. The force acting on the quartz element generates at the output of the sensor a proportional electric charge, which is converted by the series connected measuring amplifier into a process signal suitable for evaluation. The LVDT is used to determine if the press was successful. The distance a key is pressed is measured to ensure it is fully seated into the slot and will fit in the gear. The LVDT is mounted on the side of the press, and the extension rests on the plate extending from press head that travels downward. Some safety components that we incorporate are used to protect operators, shafts, and equipment from damage. As seen in previous pictures, we have a cage. We have light curtains so that the operator can load the shaft, but then nothing can enter the open slot after that while the machine is in process. We have a gate safety switch with a tag-out lockout, force sensors and distance sensors, and an e-stop. Here you can see the LVDT and load cell connection with the mounting plate for the LVDT and the distance plate. So as the press travels down, the LVDT will extend with the press head to measure the distance. The load cell is sandwiched in between the adapter and the press head so that it is an inline measurement of the press force. Here is the final product before the cage has been put on with the key bowl. And here's the final product with the cage, with the cutout slot in the front, and the light sensors, and the enclosure mounted on the very front, with the HMI screen that can be used for manual control, and the press monitor. And here's the final product with the enclosure open.